This is experiment 1 for physics 2, laboratory and recitation. And we're going to be looking at Archimedes' principle. We're going to actually test Archimedes' principle and show that it's valid for a number of submerged objects. So Archimedes was a Greek mathematician, physicist, and engineer. Not much is known about him. There aren't a lot of direct writings about him, but he lived sometime in the 3rd century BC. And he's thought to be responsible for the concept of a buoyant force, that is the force that a fluid will exert on an object, causing it to float, or at least opposing the force of its weight. And Archimedes' principle can be thought of as almost an addition or a specific case of Newton's third law. Newton's third law states that for every action, there is an equal and opposite reaction. For Archimedes' principle, we can envision an object becoming submerged. As it is submerged, it puts a force on the fluid. It displaces the fluid. For every action, this is the force on the fluid, there is an equal and opposite reaction. The object pushes the fluid downward. The buoyant force pushes the object upward. And that's essentially how we get Archimedes' principle. Now, obviously, Archimedes came long before Newton. So we would say that Archimedes came up with a specific case of action-reaction for fluids. And of course, Newton came up with his general law later on. But again, it's important to note a few things. The buoyant force, the force that buoys up an object, okay, this buoyant force, okay, is not equal to the weight of the object. Rather, it is equal to the weight of the fluid which is being displaced by the object. And that's very important, because if it were equal to the weight of the object that was doing the displacement, then everything would float. In this case, it's really what is the water, for the case of it's in water, or what is the weight of the fluid which is now being occupied by the object. So we're going to try to demonstrate this. We're going to try to prove that this is true. And again, think about it this way. We want to measure the buoyant force, and then we want to show that the weight of an equal amount of fluid displaced by the object is going to be equal to that force. Weight is a force, okay? So what is the source of this buoyant force? Well, we actually have to look at an earlier concept that we covered in fluids. That is that the pressure exerted by a fluid is equal to the atmospheric pressure. So for instance, the atmospheric pressure would be normally about 10 to the 5th pascals, okay? Plus the weight due to the fluid. And let me change that, because I think Y implies something a little bit different. We'll use H instead. Basically, how deep you are into the fluid, that'll be the H right here, will determine how much your pressure is increased due to the weight of the fluid above it. So for instance, at the very top surface of this object, in this case, we submerged a bowling ball, we can imagine that it is being pushed harder than just the pressure of atmospheric fluid due to the weight of the overlying fluid above it. So that red area represents fluid that is on top of the top surface of the ball, which is adding additional pressure to the ball, pushing it downward. Now, if we then look at the bottom of the ball, okay, so this bottom surface right here, this location right here, and again, that's versus this location right here, okay? We'll now look at how much fluid we have above that surface. And even though, there's a bowling ball above this bottom surface of the bowling ball, remember Pascal's principle says that any change in the pressure okay, is transmitted undiminished throughout the fluid. So, this section right here is pushing down on the rest of the fluid, increasing the pressure. So you can clearly see the pressure is going to be greater on the bottom than it is going to be on the top. We know that, of course, pressure is equal to force divided by area, right? So our force, our buoyant force, is going to be equal to the pressure difference between the top and bottom surface times the surface area of the object, okay? Now, how is this connected to volume? Well, we think about this here, all right? We're looking at this difference in height, so that's one dimension. If we multiply that by an area, okay, we will get area times a length is going to be volume. If you just look at dimensional analysis, again, we are going to get a greater force for the more volume that we displace, and that's Archimedes' principle. So again, we can say, for instance, what is the buoyant force is equal to the weight of the water displaced. We can say why the buoyant force exists. It exists because the pressure on the bottom of a floating object or submerged object is going to be greater than the pressure on the top of the floating object, and therefore that pressure difference is going to create a net upward force, okay, the buoyant force. And here we can see again, this bowling ball, of course, is submerged. Let's say that its density is greater than water, so therefore its weight is going to be greater than the buoyant force. And whether an object floats or sinks is entirely up to the fact that if the average density of the object, okay, you've got to basically integrate over the entire volume, but let's say it's homogeneous, so we don't have to worry about crazy stuff like that. If the mean density of the object is greater than the mean density of the fluid in which it's immersed, it's going to sink. Because what that's going to do is it's going to make the weight of the object greater than the buoyant force. Objects will float if their mean density, and again, that's mean density integrated over the entire volume, is less than the density of the fluid. And that certainly explains why ships will float. Even though ships can be made out of materials like steel, the steel is only found in the hull. Most of the interior of the boat, which is below the waterline, is going to be in fact air, which is a much lower density. So therefore, a ship will sink into the water, not sink, but sink into the water until it displaces an equal amount of weight of water to its own weight. And again, we can understand the buoyant force as being equal to the weight of the fluid which has been displaced. So let's put a few different ideas together. So for instance, the buoyant force, okay? If we want to talk about the buoyant force, it's going to be equal to the weight of the fluid displaced. Now, we know that mass is equal to density times volume, because density is mass divided by volume. So the mass of the water displaced is the density of the fluid times the volume of the object which is displacing the water. If we take mass times the acceleration of gravity, we get the weight. So therefore, this first equation represents the weight of the fluid displaced. That is the upward buoyant force. The downward force, the weight of the object, is simply the mass of the object times the acceleration of gravity. But again, we can use density and volume to replace mass. And we do that right here. So the density of the object times the volume of the object. Again, we're talking about what is the downward force on the submerged object. we take the density times the volume, we multiply that times the acceleration of gravity, and we get the weight. Okay, be careful here because notice one is density of the object, that is the weight, and the other one is the density of the fluid, that is the buoyant force. Buoyant force, weight of the fluid displaced, weight of the object which is submerged. If we're submerging an object or partially submerging an object, actually, this is fully submerged. For a fully submerged object, which we're going to do in this lab, the net force will be the upward buoyant force minus the downward weight. Basically, that negative sign indicates a downward force, the buoyant force indicates an upward force. So we can simplify this to say, okay, the buoyant force is the density of the fluid times the volume of the object times acceleration of gravity. The weight is the density of the object times the volume of the object times acceleration of gravity. So we can simplify it to be the difference in density, okay, the difference in density times the volume of the object times acceleration of gravity is going to give you the net force on the object. And again, if the object is floating, this net force is zero. If the object is submerged and this force is not zero, it's going to keep sinking further and further. A net upward force, okay, a net positive force here indicates that the object is going to go upward, it's going to float. A net downward force indicates a sinking force, or a net force, which is going to cause it to sink. Okay, so in this experiment, one of the first things that we're going to do is we're going to take some object which is denser than water. Okay, I'm going to take perhaps a metal ball. We're going to put that in a graduated cylinder. We start out with some known water level. Okay, we carefully place the ball in the water. Now, when I say carefully, it's very important here. If I just drop this ball into the graduated cylinder, it's going to fall very, very quickly and probably shatter the thing. So I'm going to, probably tip it on an angle and let it slowly settle to the bottom, and that will displace this much water. Okay. Once I'm done with that, I'll remove the ball in the water after marking the initial position and marking the final position. Okay. After I have both those values, I will refill the graduated cylinder and weigh it at this level and weigh it at the new level where the water is displaced. This is important because it allows me to directly measure how much water is displaced in terms of its weight. Okay, the buoyant force is truly equal to the weight of the water displaced. This weight here should be equal to the upward buoyant force, which is going to act on that ball when it's submerged. Now, to do this whole experiment, we are going to measure the mass of the object dry and measure the mass of the object submerged. Okay. Now, truly, if we're measuring mass, we're measuring the amount of matter, and the mass of the ball doesn't change. What does change is actually the force. So when I measure the mass of the object, okay, I'm using its weight to then convert that back into a mass. When I submerge it, however, I'm actually getting an effective mass. Okay, it's not really the mass, but again, I'm using a force, the net force on the mass as it's submerged to get what is an effective mass. Now, let's take a look at the math here. Again, this is the object's weight, mass times acceleration of gravity. So in fact, when the scale determines mass, what it is actually doing is it's saying, I know the mass of the object because I am reading a force, okay? I'm reading a force which is equal to the weight, and to do the conversion, I'll divide it by the acceleration of gravity. Okay, so that's the weight of the object. When I get an effective mass, it's not really a mass at all. It represents the net force acting on the bob, again, divided by the acceleration of gravity. Okay? Now, the neat thing about these scales is you can either place something on top of them or you can put a hook underneath them, and it will measure each force, each downward force, and again, convert it to a mass. So how do I get the buoyant force here? Well, if I know the object's weight from this, okay, and I know the net force when it's submerged, I can take the difference between the two, and that's going to be the buoyant force. Think about this. If there's no buoyant force, we just get weight. So I'm going to be able to take m0 times acceleration of gravity and calculate that weight. If I then submerge it and get that effective mass, okay, times g, that is actually equal to the buoyant force pushing up minus the weight. In fact, if we're more careful about this, we would actually say it's equal to the weight minus the buoyant force, because the scale gives you a value for it in the downward direction. So we are going to use the actual weight of the displaced water and then compare it to this buoyant force. Now, in the next part of the experiment, I know part 1 and part 2 are actually together. Part 1, you're actually doing the experiment. Part 2, you're using the data to convert it to a specific gravity. In what is labeled part 3 of the experiment, we're going to use the density of an object which is less than that of the fluid, something that would normally float. Now, the problem with this is if it wants to float, we have to do something to keep it from floating. So we're going to take a piece of wood here, which density of the wood is less than the density of the water. We're going to attach a sinker to it, okay? And we are going to perform the same measurement before and after. And the difference between the unsubmerged wood and the submerged wood weight, including the sinker, which is going to be submerged during the entire time, that difference is going to be equal to the buoyant force. And again, we're measuring an effective mass here, folks. You know, be very cognizant of that. The scale gives you a mass based on the force that it is receiving, okay? The part of the experiment that we will not be performing, this is actually part 4, sorry about that, is if we use a density of a liquid which is greater than water, and we do this calculation again, we can use the measurements that we made earlier, okay, to then go back and find out, well, what is the density of the fluid? If the fluid is greater than that of water, it's going to be more than 1 kilogram, I'm sorry, 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter. And of course, the buoyant force, I should have used a fluid here, should have used Neff right here. The buoyant force is going to be greater if we use something like salt water, and we would actually be able to measure that, but we're going to skip part 4. Okay, so when you look at the experimental write-up, we're now going to look at the experimental procedure. You can see the first part says direct measurement of Archimedes' principle. Choose a metallic sphere. I've chosen a steel sphere here. Weigh it and record its mass, m0, and the type of metal. So as you can see in the next picture, I've recorded it, and of course it was steel, which is an alloy of iron. It should have about the same density as iron. And here it is. There's the actual measurement that was performed. It's a steel sphere. It has a hole through it and a string. We're going to use a string because we're going to suspend it underneath the scale, okay? Now it's sitting on top of the scale, but if you turn the scale over, you would see that there's actually a hook attached to it, and that hook allows you to hang things off of it, and you can still measure the effective mass. So we found out the mass of the steel sphere. And now we perform the displaced water part. And again, we are going to measure the mass of the water, okay? For the first case where it's just at some level, I picked, an easy one, 50 milliliters. And then we're going to displace the water with this sphere, okay? Mark the new location and then remove the sphere and fill it up to that new level. So here's the original level, here's the new level. And of course, if I take the difference between this weight, okay, M prime W, and this weight, actually it would be times G, that would give you the mass of the displaced water, which would give you the weight of the displaced water. So let's go ahead and do that. Here is our mark. And of course, I said I picked 50 milliliters as a starting point. I measured the mass of the water and the cylinder. I know it says MW, but really this is the graduated cylinder. It's mass when it's filled to 50 milliliters. And there it is. You can see there's my 50 milliliter mark. Okay. I tried to be as accurate as possible. So when you're writing up the lab, you can talk about some uncertainty. There's a little water on the sides. That doesn't really add to any appreciable mass. In fact, that excess mass is much less than the sensitivity of the scale. And here you can see I've taken the 50 milliliters of water and I've measured its mass. Okay, so that's MW. Now I record the new mark, right? And I'm going to measure the mass of the cylinder filled to the new water level after I remove the sphere. And I take the difference between my second and first measurement, okay? And that will give me the mass of the displaced water. So here we can see the new mass. We're now at 194 with that extra water. Notice there's no sphere sitting inside here. I've removed it, so I don't have that as part of the measurement. And this difference and this difference is going to give you, oops, I'm skipping around too much, is going to give you this mass of the displaced water. Okay? All right. So once again, think about this. My first reading, this effective mass, I'm sorry, the first reading is the direct mass. And again, what the scale is really measuring is M0 times G, okay? That's the weight of the object. You can see my setup right here. It's hard to see, but again, this is the same scale. You can see it from the top here in this picture, but there's a little hook. Actually, let me use a different color there. There's a little hook here, okay, that the string is then attached to. So the string just ties in right here and attaches to the sphere. And because there's no water there, that sphere is just hanging out right here. Okay, so I measure that mass. Okay, 67 grams. I actually measured this twice. Remember in the beginning, let me go back a few slides. All right, you see the 67 grams. I wanted to make sure that the scale was working fine and that the hook and the string, which I tear it out for, don't affect the measurements that I make. So there it is unsubmerged. So that gives me my actual mass, M0, the mass of the object. And now I'm going to measure the mass of the object when it's submerged, because again, this is the effective mass, okay? This M prime 0 is not actually measuring the mass of it. It's measuring the force, okay, the net force, that is the weight minus the buoyant force, okay? And then we divide that by the acceleration of gravity and we get and effective mass. So once again, once it's submerged, we're going to have some net force acting on the scale, okay? It is going to be the object's weight pulling down minus the buoyant force pulling up, and that gives us m prime 0. And there it's submerged. And here you can see the measurement. It looks like the scale is sitting on the table. It's not. This is actually, when we look the second, we're actually looking down at the scale. The way that I've taken the picture, it's sort of an illusion. But this scale is actually above the beaker, and the beaker is right below it. Okay? And you can clearly see how that's set up right here. The reason why I show you the two pictures is this shows you the setup. This actually shows you the reading that I get. All right? Clearly, the effective mass is less than the actual mass of the sphere. Okay? We've reduced our reading here. We're down to 59. So in doing the calculations, we can calculate the buoyant force by taking how much mass we had when it was dry, how much effective mass the scale read when it was submerged, multiply that times the acceleration of gravity, and that will give me the buoyant force. What also gives me the buoyant force is the difference in the graduated cylinder when it's filled to 50 milliliters and the graduated cylinder where it's filled to 50 milliliters plus the displaced water. Okay? And that gives me this term right here. So what you're going to do is actually compare the buoyant force measured through the scale, okay, where we had the suspended mass, unsubmerged and submerged, unsubmerged and submerged. And you're going to compare that to the buoyant force calculated from the weight of the water displaced, which is the mass of the graduated cylinder filled with the displaced water minus the mass of the graduated cylinder with the 50 milliliters times acceleration of gravity. So compute those two, do a percent difference, okay? Remember percent difference? Percent difference, when we do percent difference, we take two experimental values, 1 and 2. I'm sorry. Sometimes when I talk, I can't think at the same time. It's actually the difference between the two. You take the absolute value, and then you divide that by the average value of the two. Okay? Of course, this is divided by 2. So you are essentially, with this percent difference, if it's low enough, establishing that, yes, in fact, the actual water that I measure with the graduated cylinder part of the experiment, the weight of that water is equal to the buoyant force that I got from the next part of the experiment, where we had the bob outside of the water and inside of the water. Now, going to the next part. That was part 1. Part 2, you're just doing a calculation. You're calculating specific gravity. And specific gravity is basically just the density of an object as it compares to water. Okay? Now, basically, we know that the weight of the object divided by the weight of the water displaced, the weight of the water, is going to give you a comparison of the density, right? Because the weight is equal to the mass times acceleration of gravity. The mass is equal to the density times the volume times acceleration of gravity. And when we do this, because the volume and the acceleration of gravity are the same, the ratio just becomes the ratio of the density of the object to the density of the water. So in calculating this, we can take the mass of the object and divide it by the mass of the object minus the effective mass of the object, which of course we showed was the buoyant force. Really, the weight of the object divided by the buoyant force would have a g in the numerator and denominator, but those of course cancel out. So what was the original mass? What was the difference in mass? That'll give you the specific gravity. And you should compare that, you should compare whatever your calculation is to, since we used iron right here, we're going to use 7.87 for specific gravity. Again, do a percent, but this time percent error is going to be equal to, oh, by the way, when I did percent difference, you got to multiply by 100%. So this is going to be equal to the experimental value minus the accepted value over the accepted, and what I left out was 100%. Okay, so whatever value you get right here, it better be pretty close to 7.87. Let me just go back to this one right here. And again, I'm going to rewrite percent difference. And now I'm going to include, again, E1 minus E2. Doesn't matter which order you put those in. E1 plus E2. Okay, then times 100%. I don't think I included the 100%. So that's part one and part two of the experiment. Let's go to the next part. Now we're going to do a density of an object which is less dense than water. We're going to use wood. So we'll start out by, again, measuring the mass of the wood. Okay, the mass of the object, MO. And there's my little piece of wood right there. I measure its mass. I get the value that you see. And then after doing that, I will submerge it. Okay, and here's the difficult part of this. Actually, it's not that difficult, but here's something that you should think about when we're doing this. When we're doing mass here, we're actually measuring the mass of the wood, but so it doesn't float, we need to attach a much more dense metal sinker on the bottom of it. So when I calculate the effective mass is actually going to be the weight of the sinker and the wooden sphere minus any buoyant forces. Okay, so let's look and see why this is more complicated than we think. Our net force for our first measurement is represented by the weight of the wood object, first of all, okay, and the weight of the sinker, but the sinker is submerged so there's going to be a buoyant force acting on it, okay? Now, I'm not going to go into this too much, but this force is the same for the first and second part, and because we take the difference, okay, that figure is going to subtract out, and the metal sinker will have no effect on the final measurements or the final calculations. But again, remember the net force is the weight, okay, minus any buoyant force. So we make that first measurement, M1, okay? And here you can see the sinker is below the water. I know it actually appears like the sinker is floating above, but the sinker is totally immersed, and the wood is outside the water, and this is the weight of the wood and the sinker. Now, you're going to take the difference between that measurement, okay, and my next measurement, M2, when both are going to be submerged, okay? When I fill the water up higher, now I will have an extra buoyant force, due to the buoyant force acting on the wooden mass. Again, the sinker hasn't changed. Okay, so I'm going to take the difference between this situation, okay, where this metal sinker is submerged and the wooden mass isn't submerged, and this one where the metal sinker is submerged again, and now the wooden mass is submerged. So the difference between those two measurements is going to give you the buoyant force. Again, the metal sphere is just going to subtract out. So here you can see now both are submerged, and I get a new measurement, okay? So it's going to be the difference between this measurement and this measurement. And that will allow you to calculate, let me just go up one more. That'll allow you to calculate the mass of the two. So basically, I think I have to jump back one more. I just want to make sure that I'm doing this correctly. You had M1, that was your first measurement, okay? You record M2, and to calculate the specific gravity of the wood, you take the wood's original mass, okay? Then take the difference between your two measurements, and the difference between the two measurements represents the buoyant force divided by the acceleration of gravity. So the specific gravity, again, is really the weight of the object divided by the buoyant force, okay? It's comparing it again to water. All right. For the wood, you want to compare this measurement that you get, and it better be less than 1, because otherwise it wouldn't try to float. And you're going to compare it to these different values for wood. I think in the lab, they only give you pine and oak. I've given you some more, values, and see what it comes closest to, because most of the wood that we have are either pine, spruce, or oak. Again, pine and spruce are very, very close to one another, as is cedar. But what you should be able to differentiate is whether it's some type of conifer like pine, cedar, or spruce, or whether it's oak. You probably can't differentiate because of the ranges within these, okay? So in any case, that's basically the experiment. So good luck with that. And you can just, reverse this video to find any of the different measurements that you need. But, please read the actual experimental write-up too, to make sure you don't miss anything. And finally, when you write this thing up, there are some questions at the end that you do need to answer.